All right.
So let's see.
What are they seeing, Josh?
We're seeing that.
This.
Oh, you are? Okay. You figured out how to do all of the things at once.
Oh my.
We're going to do this. Yeah, you can hold it or you can clip it.
Yeah, I'll clip it.
Okay. And then just press the button on the front and it will turn.
Oh, okay. All right. Can everyone hear me? Great. So thanks so much for the opportunity to speak here. I'll be talking today about how we're extracting useful magnetic and geophysical information from ancient rocks by leveraging hydrothermal alteration, with special emphasis, of course, given the session on how magnetic microscopy can aid in that process. And just before I start, I'll note that the irony is not lost on me that I'm going to be talking all about hydrothermal alteration right before a coffee break. So again, I hope that I can convince you guys that these geological hydrothermal fluids are a little more exciting than the ones that are sitting there waiting to be drank in a few minutes. So with that out of the way, I'll start just by overviewing the broader set of questions that I'm interested in solving. So I'm trying to use paleomagnetism to look at geodynamics during the Archean eon for about 2.5 billion years ago or so. And there are a lot of outstanding questions here. So for one, there's substantial debate over whether plate tectonics was in operation by this time in Earth history, or alternatively, something totally different and exotic, like stagnant lid geodynamics, like we see on other planets with no mobile plates. And paleomagnetism is really ideally positioned to address this problem, right? Because it enables paleogeographic reconstructions that can quantify the geometry and rates of plate motions, or the lack thereof. And of course, paleomagnetism can look even more directly at the geophysics of the very deep Earth by recording the geodynamo. And due to the probable lack of an inner core this long ago, a number of competing theories have emerged for how to drive this ancient dynamo. And those include light element exsolution. My, it's vibrating a lot.
You'll see it.
What? Okay. Yeah. If this is too annoying for people, I can just press a button and turn that off. But what do we think? Okay. Oh, now it's okay. Anyway, apologies for that. But there are a number of different possible mechanisms to drive the ancient dynamo this far back in Earth history. It may include light element exsolution out of the core and into the mantle. And even actually proposals of a rapidly convecting basal magma ocean that was just barely conductive enough to produce a field that's detectable at the surface. Okay, with all these grand sort of questions in mind, my goal here is to show you that something as small scale as magnetic microscopy can actually be really helpful in solving these large scale geophysical kind of problems. And that starts with going into the field to sample some Archean rocks, right? And look for Archean remnances. But as anyone who has seen Archean rocks in the field can attest, there are some challenges inherent to working on these rocks. And foremost among them is just that very few of them survive today, right? That's because later plate tectonic processes have obliterated all but about 5% of surface rocks that date to the Archean. And as Tim so eloquently pointed out yesterday, what few rocks do remain have endured great offenses on their journey from the Archean to the present day. They've been affected by metamorphism, deformation, and alteration, like, for instance, the rocks in this picture. And all of those processes can overprint or even erase paleomagnetic information. So studying these Archean rocks and successions demands of us really extreme care in selecting the samples that are most likely to preserve remnants as well, and also in understanding the full mechanism and timing of those remnances. And so thus far, my field area of choice for performing this kind of work has been in the Pilbara Craton in Western Australia. It's one of the best preserved fragments of Archean crust, and that's because it has, relatively speaking, low metamorphic grade rocks up to 3.5 billion years old or so. And so far, we've sampled about 10 different formations here for paleomagnetism with various success, spanning almost 800 million years of the Archean rock record. And today, I'll just be focusing on one of those formations. It's called the Cunnagunarina Formation. Say that 3 times fast, right? It's a package of basaltic and komatiitic lavas, so mafic lavas, that are about 3.25 billion years old. And in this picture, I'm just highlighting some of the mafic flows and tephra beds with the white dashed lines and arrows here. So we went here in 2018, sampled these lavas for paleomag. And as expected for really old basalts, we ended up getting a bunch of samples, some of which preserved some multi-component magnetite hosted remnants like these two here. And some of the components here are overprints, as expected, that correspond nicely to various overprinting events from present day to 2.78 billion years ago. And there's also this highest temperature component in orange that may be the characteristic remnants that we're after. So now, again, given the complex histories of these rocks, we have to really be careful to contextualize that remnants if we're to make any claims based on that. And the first step is to identify how the grains carrying it formed. And working in Roger's lab and being in a magnetic imaging session, our tool of choice for doing so is naturally the QDM, shaking still. And what it does is it just images, again, the magnetic field and thus the locations of magnetized phases on the surface of our samples at about micron scale. And so we can look at a bunch of mineral textures in our samples using conventional microscopy, and then use the QDM on top of that to image how the remnants carrying magnetite in these samples interacts with those textures. Essentially, we're performing magnetic petrography that can link these magnetized phases to specific primary or secondary features in our samples. And as you'll see, this is a really powerful capability without having to perform any inversions or do any additional math. It's very qualitative and still powerful. So what did we find when we looked at all of our samples using this? Well, so for instance, here I'm showing a transmitted light image of a pyroxene phenocryst in one of our samples. So I've overlaid atop this image a quantum diamond microscope map of the magnetic field over the sample. So those are the reds and blues that just correspond to magnetic field, again, pointing out of versus into the screen. And that shows, again, where all of the magnetites are. Wherever you see little, blue and red dots, those are predominantly magnetites in this sample. So while the pyroxene crystal itself, this tan color, is a primary mineral that formed during cooling of the lavas themselves, the magnetite in this case is actually concentrated along the rim and in fractures inside of that pyroxene phenocryst, where that pyroxene has been altered hydrously to actinolite and chlorite. And I've just labeled those hydrous phases in green here just to differentiate them from primary phases. So this magnetite is pretty clearly associated with hydrous alteration of pre-existing ferromagnesian silicate minerals, likely in this case via serpentinization-like reactions. And here's another pretty clear example of one of these textures. So these images show chromites. So again, a non-magnetic mineral that would have also formed along with the cooling of the lavas, but these two have been altered and they've been metasomatized into chromium-rich magnetite. And sometimes they even, like this one on the right, display really porous hydrothermally generated textures. And as a result, they're all very strongly magnetic now, as is very visible in the overlaid QDM maps here. And so just to summarize both of those examples, they're cases where hydrous alteration of primary non-magnetic phases led to growth of magnetite, and much of that magnetite survives today. And of course, our observations of these textures are a lot more complex than I have time to really cover in any detail, hence the great deal of detail on individual minerals in this figure. But the key point to take away is not all of the minutiae, right? It's that there's this diverse group of reactions and paragenetic sequences and mineral assemblages that all end up making magnetite under these kinds of conditions. And in many samples, we actually also observed the surviving remnants of titanomagnetite grains, which would have been the primary magnetic minerals that formed with these lavas during cooling. And they're often pretty coarse, but occasionally, like in these examples, they're quite delicately preserved and preserve things like interrupted dendrites, ladder-like arrangements, little strings of tiny crystals, all composed of nearly pure magnetite. And these features are all pretty consistent with primary titanomagnetite dendrites that have been mostly dissolved and then recrystallized or encrusted with this now very low titanium magnetite that's more stable in hydrothermal settings. And so that adds to that last set of observations. And that's because of course, these primary iron oxide phases are by no means exempt from any of the alteration processes that are going on around them. And despite again, the complexities of the reactions that are involved, they also end up altering to magnetite that we can measure. But perhaps the most important insights in these rocks came from looking at vesicles that formed within the lavas again as they cooled. And these vesicles are informative because when hydrothermal fluids percolate through rocks, they tend to precipitate minerals into void spaces like these vesicles. And those minerals reflect the composition and thermodynamic conditions that prevail in the fluids. And so in our samples, what this manifested as was a very clear 4-stage prograde paragenetic sequence. And I'm just highlighting those on the left with the numbers and colors and their associated temperature constraints. And some of these stages, especially stage 2 in the orange, are associated with some quite strong magnetizations that are visible in the QDM maps. And it turns out that specific stage, when you do electron microscopy on it, it's full of these little tiny exolved magnetite needles that came exolved out of silicates that themselves precipitated at about 250 to 320 Celsius, give or take. And this stage ends up hosting a pretty substantial fraction of the magnetization in this particular sample. And so again, one more time with, all of this here adding to our sort of holistic alteration picture. And again, ignore all the minutia of what minerals are reacting to make what. The point here is that this complex series of reactions ends up making and then preserving magnetite. And this time it's purely just from dissolution and then reprecipitation of iron-bearing phases in the surrounding rocks. And in fact, with that specific assemblage of really strongly magnetized stuff, that stage 2 stuff in orange, we're actually able to show that that strongly magnetized material within those vesicles, the magnetite inside it has the same unblocking temperature range as corresponding bulk samples that we measured on a 2G. And we demonstrated this by imaging the material with the QDM and then tracking how the surface pattern of its magnetic field changed during progressive demagnetization. So the way that works in practice is, again, we identify an example of this, this texturally defined magnetite in a vesicle. We image it in NRM. And we identify, I've just drawn them in the thin white lines here, positive patches of surface field on that map. And then as we then demagnetize a step and image it again multiple times, we then keep track of what percentage of the area in those white areas that were initially all positive remain positive. And once you get to the point where there's 50-50 positive and negative. In other words, it has those original areas have no bearing on the current state of the field. You're approximating what's happened with the sample demagnetizing entirely. And so what we can see is that, again, this is basically, think of it almost like a J over J naught curve, right? So in the sort of 520 to 560 Celsius range, where the corresponding bulk sample to this example that we're demagnetizing here, where it loses almost all of its moment to this component that we're really interested in, you see the exact same thing in this particular phase assemblage. And so the important thing is just to show, again, that the magnetization of this sample that we can, again, measure on a magnetometer traditionally is directly tied to some of these secondary minerals that form via hydrous alteration. And that strongly suggests that this is a chemical remnants that we're maybe looking at. So now that we understand how the remnants carrying magnetites formed, we have to determine when they formed, right? And the hydrothermal alteration that produced this magnetite in our rocks could have in principle occurred anytime after the rock's formation. And it's for this reason that most paleomagnetists, not all, but most, usually try to avoid interpreting chemical remnants like these. They're just not as straightforwardly datable as, say, the formation of rocks themselves. And so in order to be successful, we have to narrow down where in that last 3.25 billion years this alteration has occurred. And of course, paleomagnetic field tests, traditional field tests apply here, right? And fortunately, we can get most of the way back to the Paleo-Archean by leveraging a positive fold test on a 2.9 billion year old structure. But that still leaves 300 million years of ambiguity, right? And we all know that a lot can happen to rocks in 300 million years. And luckily, some of our samples actually contained a datable mineral formed by the hydrothermal alteration itself. It's these bright white rhombus-shaped mineral grains called titanite. And not only is titanite datable using the uranium lead system, we are actually able to show in our rocks that texturally, these titanites formed after all of the magnetite producing reactions in our rocks. So if we can date these, they provide a lower bound on the age of magnetite formation. And here are the results of that. So for those of you who may not be familiar, this is a Terra-Wasserberg Concordia plot. And if you've ever seen a traditional Concordia diagram for like zircon geochronology, it's not quite read in the same way. And it's especially true for titanites because titanites, unlike zircons, incorporate variable amounts of common lead from their environment during crystallization. And that means that the uranium lead composition of a population of titanites that all crystallize at the same time will lie along a linear array, which, as you can see, our titanites do. And the important feature of that linear array is its lower intercept with this white curve, the Concordia curve, which gives the age of that array, which in our case ended up being over 3.2 billion years old. And that we can add to our timeline. And as you can see, that really pins down that age of, again, magnetite formation quite nicely. And in fact, we actually were able to use this to confidently assign the magnetite formation in our rocks to a specific set of documented seafloor hydrothermal events that all occurred within 20 million years after the eruption of our lavas. So what's also important to note is that there aren't any geological events between this 3.2 billion year old range and 2.9 billion years old at the fold test that could have overprinted the magnetite we've dated in a way that would make the remnants direction and characteristics that we've isolated. And so this magnetite is in fact actually preserving a chemical remnants or CRM from the seafloor during hydrothermalism about 3.25 billion years ago. So even though our rocks are, again, extensively altered, right, they have no trace of any of the sort of primary magnetic signals that people are after, right, primary TRMs, we are still able to use their magnetizations anyway for our paleogeographic work, as I'll get to. And that's because we could directly tie these magnetizations to alteration that can itself be directly dated. And so now that we know what event formed our magnetizations, we can look at it and understand it better. So as I mentioned briefly in the text there, this system is this alteration is part of a volcanic-hosted massive sulfide or VHMS system. And this is where a large magmatic heat source heats a package of overlying rocks from below and sets up the conditions required for convective circulation of seawater through the whole rock package. And as that seawater flows through the rocks at temperatures up to a few hundred Celsius, it dumps some of its dissolved elements and picks up others from the rocks along the way. And it essentially marinates the rocks to make new minerals. And our rocks happen to be on the margins of what is actually one of the best preserved examples of a VHMS system anywhere in the rock record. It's called the Panorama District. And what we're seeing is just the end product of all of these alteration processes. And those end products bring those mineralogical changes that we've observed into sharper focus because these VHMS systems generally have predictable depth and lateral zonation of alteration facies. And depending on where you are in that seafloor hydrothermal system, in the volume of rock that's actually getting altered, the alteration processes and reactions change alongside the prevailing conditions of pH, temperature, depth, and water to rock interaction ratio. And the conditions that favor magnetite growth and preservation are in the deeper actinolytic and procolytic facies within these systems, and that's like where we sampled. And the reason for that is that the pH is circumneutral, it's rock buffered rather than being quite acidic. And also there's relatively speaking, limited water to rock interaction, which limits the amount of leaching of iron out of the rocks, which would promote the dissolution of magnetite. And what's great about this zonation is that it's actually really obvious in hand samples, as you can see over there on the left. The magnetite-bearing rocks are darker because they've lost minimal iron. And so targeting the right samples in the field becomes very straightforward. It also just gives sort of some meaning and motivation behind that traditional kind of paleomagnetic sampling field instinct of, ooh, that rock is darker, let's sample that one instead. At least for this specific type of system, this is why. So at long last, So we're now ready to discuss all of those geophysics questions that we did all of this to answer. And the answers, I think, are some pretty exciting stuff. So for one, there are actually two packages of altered volcanics in this formation that we sampled, and they happen to sample across a geomagnetic reversal. And it's actually the oldest relatively robust example of a geomagnetic reversal that's been documented so far. And further, because this reversal is relatively symmetric, suggesting a very dipolar field, that suggests that the dynamo that was producing this field was likely produced in a low aspect ratio field generating region, in other words, the core, and probably not a thin shell basal magma ocean dynamo, as has again been proposed for the early Earth. And regardless of what's driving the dynamo, we now have a hint of empirical support that we're actually measuring a geocentric axial dipolar field, which is, of course, great news for using paleomagnetism as a paleogeographic tool. So now that we have all of this confidence renewed in our paleofield geometry for this far back, we can move forward even more confidently with tectonic reconstructions as well. And for those, together with two other paleopoles from the East Pilbara, this resulted in the oldest time-resolved motion reconstruction that's been documented so far. And what's very clear is that the East Pilbara was experiencing tens of millions of years of very large motions during this interval of time that we're interrogating in the Archean. Including a latitudinal translation and then a rotation, both occurring at about 0.5 degree per million years, or equivalently about 6 centimeters a year. And so motions like that, that are prolonged, relatively fast and capable of changing directions in this way, are pretty difficult to reconcile with pretty much anything other than plate tectonics. And so it would appear that something like plate motion was probably occurring on Earth by 3.3, 3.2 billion years ago based on this. So this is, of course, ongoing work, and there are so many cool directions we want to take this. So for instance, it's one thing to be able to collect some samples and analyze all of these things after the fact, after the sampling. But what if we can use other data sets to maybe target this, look for this alteration beforehand and target it during sampling? So along those lines, we're collaborating with a remote sensing specialist at JPL named Adrian Brown, and he's done aerial hyperspectral imaging of some areas in the East Pilbara. And that takes what would, a satellite image like this that would just show a featureless sea of altered basalt, and it turns it into this huge tapestry of mineralogical facies zonations, like this here on the right. And we're in the midst of a big push to work on these rocks in order to better understand and link how our paleomagnetic data are tied to these regional scale alteration features. Incidentally, all of the mentions of that EMIT program that NASA is running right now, I salivate over that EMIT data if I can get my hands on it for the areas I'm working in, because again, it's in the same sort of wavelength bands that can tell you all of these cool hydrothermal alteration features. So this, all of this has the potential to take, again, a lot of the guesswork out of sampling for these hydrothermally altered rocks and maybe get more detailed observations as a result. And we're also keen to work on modern analogs to these Archean hydrothermal systems and also other types of hydrothermal systems. And as an example of both of those, we've started working on the timing of serpentinization in a few ophiolite sequences with James Hepworth and Anthony Morris from the University of Plymouth. And finally, when it comes to all of the Archean geophysics questions we're trying to piece together, we're actively working on applying these techniques to rocks of many ages from a few different cratons at once to, one, get at the holy grail of this, which would be differential plate motion estimates, and also to push the paleogeographic record even further back into the Archean using some really well preserved and exposed basalts like these. So just to summarize again, everything that I've just presented. So our work is opening up a lot of Earth's oldest altered rocks to paleomagnetic analyses. And this is thanks to this, unique combination of techniques that we've harnessed to tie magnetizations to their mineralogical underpinnings, formation conditions, and ultimately specific geological events. And of course, key to this session is that the QDM and magnetic microscopy and imaging more generally are what enable us to combine all of those aspects into a really coherent picture. So with that, thanks so much for your time, and I'll take any questions. Yeah.
Thank you for that very interesting detailed talk. I have a very naive question for you. In the Pilbara, are there lavas that you can find that aren't hydrothermal? And how deep is, if, and in Australia, how deep is the alteration front in certain regions? And are there drill holes that can go below that alteration front so you don't have to deal with alteration?
Okay, a lot of nested questions in there and all good ones, actually. So there are rocks that haven't experienced nearly the intensity of hydrothermal alteration that we're dealing with here. I would cite, for instance, all of the extensive work that's been done on the sort of 2.7, 2.8 billion year old rocks in the Pilbara called the Fortescue group. They have all, of course, been metamorphosed, as everything in the Pilbara has, up to a point, but yeah, they haven't experienced this kind of alteration. As for the sort of alteration front, I assume you're talking about like the sort of laterization and weathering, right? So later sort of, weathering processes. So you can access some rocks that, again, like all of our rocks are surface sampled, and we're getting, all of these results just fine. So if you're careful about, like looking at all of your rocks in the field, you can often avoid that. There are definitely places though where it's deeply weathered, and there are a few isolated places where drill core is available, and people have done paleomag on some of those. For instance, one of the paleopoles that I was showing is derived from that.
Thank you very much.
Yeah, thanks a lot. I guess I have a sort of follow-up question on your assertion about the titanite and this timing relative to magnetite ontogenesis, just because I'm sort of thinking about this more, broadly, and your stopping experience CRMs, being able to have a basal phase associated with the paradigmatic sequences. I guess it seems like that's associated. You first introduced it, the titanite associated with titanium magnetite dissolution, and then autogenic titanite precipitation.
Yep.
And even in that context, you sort of talked about that leading to stoichiometric magnetite. But then you later made the assertion that the titanite is coming later, which I presume means you're taking the bulk of the magnetite. Right. So just if you could elaborate.
Yeah, absolutely. So yeah, they're texturally sort of two different populations of titanites that I'm talking about. So the first ones that you mentioned, let me see if I can get zoom out of my way so I can go to one of those slides again. The population of titanites like these, right, that are coming from, again, the titanium bearing component of titanomagnetites during this alteration. The timing of that is, I do not know exactly where in the sequence they're coming in. It's probably towards the latter end, but this is not the titanite that we're dating. It's actually really grungy looking stuff for the most part. It often contains a lot of like little interspersed titanium oxide phases, for instance. The titanites that we actually dated are from a different generation, or actually, I should say they're more produced by different reactions. So actually, you can actually see them in here. So they're coming in during the albitization and, in our case, actinolitization reactions in these rocks. And that actually ends up making a lot of sense. So there have been a few experimental studies on the albitization process that show if, say, a piece of plagioclase that hasn't been albitized yet, even one that contains, little, tiny bits of, exolved magnetite or titanomagnetite needles, right? When that albitizes, it liberates pretty much any of the titanium that it was holding onto, and combined with, all of the calcium and silica that's flowing around in the system at the same time during those reactions, you have all of the ingredients to make calcium titanium silicate titanite.
I see. And then for the ones you're actually dating in this, I guess the stage 3 is like the rim on the vesicle, basically. Are they're actually in the vesicle, the ones that are. So so in these titanites are sort of interspersed. They're coming in sort of the whole volume of any void spaces. They really like precipitating there because, again, they are a void space. But we do also find them in the matrix in certain cases, especially where that matrix has been sort of corroded away by like carbonatization reactions, for instance. Yeah.
Have the mic back.
Yeah, for sure.
So
So your Pilbara reconstruction, motion reconstruction is really fascinating, especially since it's in a 3.1, 3.2 window where a lot of people are arguing on sort of plate tectonics. I'm wondering if there's anything anomalous enough about it in terms of rates of motion, et cetera, that might speak more broadly to what plate tectonics was doing at that time, spreading rates, the presence of other continental masses, inferred subduction, production of continents, anything like that.
Yeah, absolutely. Unfortunately, we can't really say all that much with what we have so far. This is a big reason, again, why we're working on, multiple rocks of multiple ages in the Pilbara and elsewhere to, again, get at some of these questions. But for all intents and purposes, there's sort of rates and, durations that we're seeing are, again, pretty comparable to things that we see in the present day. And we can hem and haw about like, whether or not this is, representative of a more Archean situation where maybe, the mantle is hotter and convection might have been faster, but there's less basal coupling. Like there are all sorts of cool questions that we can maybe address with more data from multiple different time periods and multiple cratons.
Yeah, just on that point, I think one of the things about the bull bar, which is fascinating, and that is Martin Van Pranodonk and others have kind of pointed out that the structural style in the bull bar is different than other cratons, particularly in its 3.5 to 3.2 and perhaps younger ages, in the sense that we see these very large cylindrical structures that continue to grow for hundreds of millions of years, and he would say continue to tilt. So with that background, I'm concerned about the similarity of your directions and the Fortescue directions. Now, there are flood basalts and there are flood basalts, as Tim was kind of pointing out actually in some of his diagrams. The 2.7 event is just an incredible event around the world, and the Fortescue is part of that. Your magnetites are actually precipitating at low temperatures, right? They're now at some point or another, presumably sitting underneath the Fortescue basalts, which at some places are 7 kilometers thick. So you're going to be really hot. So I'm just wondering about this in terms of kind of normal hold tests and things like that. Is there a possibility that you have a thermal overprint, and remembering that overprints can occur in both polarities, and the Fortescue of course has 2 polarities.
Absolutely, great question. So there are a number of lines of evidence that we have against that. For one, we actually see the Fortescue as an overprint in some of our rocks. Let me again briefly go back to that. So this component right here, that is actually the sort of early Fortescue that we're seeing. We're pretty sure. The second thing is that, let me go back to one of my backup slides where I have the structure here. So this is the structure that we're sampling across. We're in sort of this area. And yes, it's quite complicated, but the age of structure formation here is one of the best pinned down of anywhere in the Pilbara, actually. It's, again, about 2.93. And the geographic, and also that's, again, way before the Fortescue. In fact, the Fortescue is actually the rocks just over here off this map, and they're more or less flat lying. So in this area, we would actually expect something like, I think it's like a 60, 70, 80 kind of degree difference between the sort of directions that we see in situ, which are very shallow for these, and the Fortescue province, which is quite steep. So yes, absolutely, the Fortescue is definitely something to worry about for the Pilbara. That said, the fact that our paleopole and the sort of Fortescue sequence paleopoles are pretty coincident is just a kind of coincidence of structure in this case.
Okay, time for coffee. Well, let's have one last question.
My question is on, are you saying that the exolved conclusions within the stage 2 are holding onto the remnants that you are ascribing to the CRM?
Yes, so again, let me go back to that.
So those are inclusions within anorthite, and the idea is the anorthite forms at the same time, stage 2.
Yeah,
And
that
then
so
add- I mean,
Go ahead.
just raise the question.
Yeah, sure.
Because I'll lose it otherwise, it's not you. Anorthite formed, containing dissolved iron within the silicate structure, and then cooled, exalting the needles, which required a recording of field. That's the model that you have.
that's a possibility, yes.
The one question I have is, there's been a fair amount of work on inclusions within these, feldspar's and
Yep.
hydroplaces, and the idea is that they're typically exalting at much higher.
Right, yeah.
Yeah, so I'd be curious to know what your thoughts are about that and why. This seems like a new mechanism for excavation
Yeah.
within these feldspars that I'm not equipment anymore.
Yeah, and the answer is that I'm not that familiar with it either. Actually, this is something really kind of extraordinary, but we're basing this on a number of different things. First off, it's just the morphology of these things growing on the edge of a vesicle. This is really reminiscent of like zeolites, for instance. And it turns out that a lot of these zeolite assemblages, if you read through the like hydrothermal alteration paragenesis literature, often co-crystallize with anorthite under the right conditions. The second thing, let me go to yet another backup slide here, is that we actually have a mineralogical sort of modern analog to this. So this is actually a diabase sill in Virginia that there are these, again, this is why I colored it in orange, because I'm used to seeing this sample that I collected years ago. But there are these little rosettes of zeolites, and sort of in between, interstitial to all of the zeolite crystals in these things, there's this, again, now albatized probably plagioclase and magnetite assemblage that's all over the place. This obviously doesn't have any of the like little exolved needles, which is like, again, the crux of the question. It's also, I suppose it's also possible that it's coming from a different co-crystallizing phase, like exolving out of, I don't know, like epidote, or if there's maybe actinolite forming very early in the sequence. This is something that I would love to be able to see more examples, but it's the only one that I've been able to find is this set of samples from Australia. Yeah.
Okay, that's all we have time for, but just a reminder, you can ask a question for all these folks at the very end of the next two talks, but yeah, so.